Now let's try to study about the chapter 9, which is about the magnetic field. So first, we are going to introduce you the concept of the magnetic poles. So you will find out later that it is very similar to the electric charges we learned before. And we are going to define the magnetic fields produced by the magnetic poles, which is the same as the electric charge produce the electric fields. And I'm going to introduce you about the magnetic domains within the materials, which is how does the bar magnet or any kind of object can produce a magnetic field. And then we are going to connect the electric current to the magnetic fields. So which means the E field we learned in the chapter 8 is not independent from the B field. So what is the magnetic poles? So if you see in the nature, we have so-called the bar magnet or the horseshoe the magnet. So you will find out that all the magnets always have the opposite poles on each. And just by convention, we call one of the poles is the north and the other pole is the south. And through the simple demonstration, people realize that the like poles repel and opposite attract. So this is very similar to the electric charge. Yeah? The same sign of the charge do not like each other, so they repel. The opposite sign of the charge attract each other. But something different compared with the electric field is that you can see an isolated electric charge, positive charge, isolated negative charge. But for the magnetic poles, you never can see one north pole or one south pole without each other. So which means no single poles known to exist. And this is one of the biggest mystery in the particle physics, and no one can still provide an explanation for that. So today we are simply going to focus on the device which always exists north pole on one end and south pole on the other end, no matter what kind of shape of the magnet it is. So let me give you about a pictorial way try to show you what I just mentioned. So if you have two bar magnets, and if you have one north pole and south pole near to each other, because opposite poles attract each other, so you will feel a force, attraction force. So in the scenario B, it simply just switch the order, yeah? But still, as long as they are the opposite poles, they attract each other. In the scenario C, you will find out if it is north and north pole near to each other, the same poles do not like each other, so it will be a repulsive forces on each other. And no matter this is north and north and south and south. And did you also notice that the force on the first bar magnet and the second bar magnet, the magnitude of the force are the same, but in opposite directions. So I hope you still remember when we studied this one in the electric field. It is due to the Newton's third law, reaction and actions. So you can consider that this bar magnet tries to act a force on them, and this one will act back to the second one. So just make sure that you remember the force here is the same in magnitude to each of the bar magnet, but in opposite position and acting on the different bar magnets. So here we see there's a force. So if you have a force, how do we understand that? So apparently we see there are two different kinds of force, attraction and the repulsions. And it is always involving with the pairs of the magnets. So you can see until now the behavior is very similar to the electric force. And also the strength of the magnetic force depends also on the distance between the two bar magnets, or in general, all the magnets. So let's try to study a little bit more. So apparently, the the magnetic poles, no matter it is the north or south pole, they can give rise or produce a magnetic force. And this force can interact with each other with different poles. So we can use the compass to measure the directions. So the compass gives you a sense of feeling that the electric force is pointing to the north pole or the south pole. This is the function of that. So therefore, they can give you the concept of the directions. And the rule for the magnetic force is basically, as we just mentioned, like poles repel and opposite poles attract. So far it is still very trivial. But now let's have the first conceptual quiz. A weak and strong magnet repel each other. Which one will have a greater forces acting on that? The answer is both the same. When we say weak and strong magnets, we mean the magnetic field produced by that. But when they try to interact with each other, the force experienced on strong and weak magnets are all the same. And it is simply due to the Newton's law. So don't be confused by the weak and the strong. Now, let's talking about the magnetic fields. So when we introduce the electric force, then we introduce you the concept of the electric field. Electric field is the electric force per charge. So the same, we have the magnetic force. So we define the so-called the magnetic fields. So what is a magnetic field? It is the way how you present how strong the magnetic fields surrounded around the magnets. And the field will reveal by the field lines. So do you remember the electric field lines? So the same thing here. So the magnetic field can be visualized by the magnetic field lines. However, now you always have the pairs of the poles. So the convention is that the magnetic field lines always comes out from the north pole. It comes out from the north pole and curve around the magnet and back to the south pole. This is a convention. And just refresh your memory. In the chapter 8, the electric field lines always comes out from the positive charge and always end at the negative charge. A very similar thing. The only difference is that now these field lines always start from the north and always end at the south. They never exist isolated. So you can find out that the field lines are always connected, and also the field lines do not intersect with each other, no matter how close they are. And finally, it's about how strong the field it is. So the way how we define the intensity of the field is based on the density of the field lines. So you can see the density of the field lines around the poles are bigger. If you are away from the poles, the density of the field lines here is much smaller. So the line closer, the bigger the field it is. So they also explain what I just say is that the further away from the bar magnet, the smaller the magnetic field it is. So now I'm going to show you a different kind of combination of the magnetic fields, like the charge. So now you have the two bar magnets. Here I show you it is north pole here, south pole here. But think about it, if in the exam, I just remove the letter N and south here, and I simply just let you see that the direction of the area of the field lines. Can you still understand that this is the north pole and this is the south pole? So remember our convention. The magnetic field line always comes out from the north pole and go back to the south pole. Okay? And now let's take a look about the different kind of configuration. If you have one north pole and south pole, you will see that because north and south like each other, so the field line will simply just connect it together. But you can see here, the field line do not like each other, so they repel each other. Now let's take a look about these configurations. So you have a south and north and south in parallel. So you will see the convention always follow that the magnetic field line comes out from the north pole and end at the south pole, and the same here. So in the future, I hope that if I don't give you the information of the south and north pole, you still can find out where they are based on the direction of the field lines. So but where are all the magnetic fields from? So we know that we have the north and south pole. However, they are not simply produced by the north and south pole. Intrinsically, the magnetic field is produced by the movement of the electron. Did you see that the movement of the electron plays a crucial role since the chapter 7 about the temperatures, the kinetic energy, and we're talking about the movement of an electron is the current. And now the electron motion can produce even the magnetic fields. So there are two different kinds of the electron motion. The first is the revolutions. So if you have an electron orbiting around the center, so this one is the so-called angular motions. They will produce the magnetic field. But the second kind of the motion is called a spin. So each electron itself will rotate along its own central axis. So they also will produce another magnetic field. So there are two main contributions to the magnetisms. So that is how the magnetic field are produced. So for example, if you have a pair of electrons spinning in the same directions, so for example, these two are both spinning in the same directions, then I will say that this kind of material has a stronger magnetic field. However, if you have pairs of electrons spinning in opposite directions, so now if this one is spinning in the counterclockwise and this one is clockwise, then the magnetic field for this kind of pairs of electrons is weaker. So that is how the magnetic field was produced. It is based on the property of the materials. Now, how can we measure the magnetic fields if we don't have the magnetic field lines? So we use a compass to measure that. So if you use a compass and showing that where is the direction of the north, and if you keep following the path, you will find out that they will lead you not to exactly the north geographic poles. They will lead you to the point which is a little bit away from the geometric poles. So people realized through the very careful measurement that the magnetic poles, south and north pole, are tilted away from the rotational axis, which is the geographical poles, by an angle 11.5. So which means the true north pole geographically we say is different from the magnetic poles. And you will see from this diagram also that is for the Earth, the position where the north geographic pole is actually the position of the south magnetic poles. This is something people usually have the illusion from. They are not the same. North geographical pole means south magnetic pole.